In this video, let us now consider two other chemical properties of alkanes. We're going to look at the addition of water known as hydration. We're also going to consider the formation of halohydrins. Halohydrins are compounds that contain the hydroxyl group and a halogen. Actually, they are alkanols that contain halogen in it. So we refer to them as what? Halohydrin. But first, let's look at the addition of water to alkanes. The reaction process known as what? Hydration. This reaction takes place by acidifying water and then reacting it with alkanes. The acid used in this case is either tetraoxosulfate 6 or you can use trioxophosphate 5-acid to acidify the water. Alright, once this is done and then the water is reacted with alkanes, it will lead to the formation of alkanols. You get that right? So the addition of water to alkanes produce alkanols. This method is actually a convenient method for preparing secondary and tertiary alkanols. Take note of that, please. When the reaction between this acidified water and alkane is with unsymmetrical alkanes. We've explained the concept of unsymmetrical alkanes. That is alkanes in which the carbon atom of the double bond, the number of hydrogens, the pair, is not equal. Is that okay? So in a situation like that, Markovnikov's rule is applied in the reaction process so as to help us know what the product is going to be like. On the board we have these two reactions. This is propane reacting with water. This H plus here is telling us that there is an acid used to catalyze the reaction in the process. As I mentioned, we can use either tetraoxosulfate 6 or we can use trioxophosphate 5 as the acid. So this compound, propane, is an unsymmetrical alkane. During the reaction, what's going to happen? Of course, as usual, water is going to split into OH negative, that is the hydroxyl, and then it also releases hydrogen ion. Is that okay? Then the hydroxyl will attach itself to this CH to give us CHOH. Why the hydrogen from the water? Following Markovnikov's rule, of course, will attach itself to CH2, making it what? CH3. Take note that these two carbons will be attacked because two of them are the carbons of the functional group. And of course, because propane is an unsymmetrical alkene, it means that the product follows Markovnikov's rule. This is a compound formed, and the name of this compound is propan-2-ol. Propan-2-ol. Alright, that's the name of this compound. Let me write it on top here. Propan-2-ol. Let's quickly look at this. But before that, anyway, this propan-2-ol is a secondary alkanol. It's a secondary alkanol. Take note, because the carbon bearing the functional group OH attached to this carbon are two alkenes, or you can say two carbons are directly attached to it, making it what? A secondary alkanol. We now look at this compound. This is 2-methylpropane. 2-methylpropane reacted with water, acidified water, and then as usual, hydrogen from this water will attach to this CH2 to make it what? CH3, and then the hydroxyl OH negative will now attach to this carbon. Is that okay? To give us this OH here. Of course, the double bond will break the single bond, and this compound known as 2-methylpropan-2-ol is formed. Alright, let me squeeze that out here and see. 2-methylpropan-2-ol is formed. It's a tertiary alkanol. It's a tertiary alkanol. So once again, take note that this addition of water to alkenes, it's a convenient method for preparing alkanol as well too. The next chemical reaction here is a reaction with chlorine or bromine water. Is that okay? The compound formed are referred to as halohydrin. As I explained earlier, they are alkanols that contains halogens. Now, what is this chlorine and bromine water? Chlorine water or bromine water is formed when chlorine or bromine react with water. And of course, these compounds are acid. We refer to them as ozochlorate 1 acid when the reaction is between chlorine and water. or we refer to it as oxobromate 1 acid when the reaction is between bromine and water. So take note of that. When you hear of bromine water or chlorine water, they are actually oxobromate 1 acid and oxochlorate 1 acid. The reaction leads to the formation of what? Halohydrins. Okay, so let us look at this chemical reactions here on the board. The first one is the reaction of propane with chlorine water. This is how it's written actually. HOCl. Yeah, HOCl. That's oxochlorate 1 acid. During the process, what happens? The OH will attach to this CH2. Is that okay? The OH will attach to this CH2, while this Cl will attach to this carbon. Because this carbon is sufficiently more negative, radically more positive than, more negative rather than this CH2. Is that okay? So this chlorine will attach there, and then this HO or OH rather will attach to this CH2. So what do you expect to get? You get an alkanol, and which you have chlorine attached to the adjacent carbon. The adjacent carbon to the carbon of the functional group will bear the halogen. That's what we'll have here. This is the carbon CH2 bearing the functional group OH. Then this chlorine is attached to the adjacent carbon. The name of this compound is 2-chloropropan-1-ol. 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 It is a primary alkanol. The primary alkanol. Like we stated, the primary halohydrin. Is that okay? Now we move on to the reaction with bromine water. Now I try to show you, the full look of the reaction between this halogen and water. This time around I didn't write HOBr anymore. It's actually meant to be like this. HOCl. HOBr, but I chose to show you this so that you understand clearly how this bromine or chlorine water is formed. For example, in this case, this bromine will split to Br and Br. Is that okay? Negative, negative. Water will split into OH, negative, and H, positive. Is that okay? Then this bromine and this hydroxyl will react to form that oxobromate 1 acid, HOBr, just like you have HOCl. Is that okay? This HBr, hydrogen bromide, is a living group. They go off. The reaction is between this bromine and hydroxyl attacking this double bond of the alkane here, of this propane. This Br and this hydroxide ion, they will attack this double bond, breaking it to single bond as usual. Then OH will attach to this carbon, CH2OH, while bromine will attach to this CH. And then we have 2-bromopropan-1-ol. This second reaction with bromine water is very, very important because it's actually used to test for unsaturation. It's used to test for unsaturation. Is that okay? For example, if alkanes pass through bromine water, the color is reddish brown, just like we treated when we carried out the reaction of alkane with hydrogen. We talked about bromine there. That bromine is reddish brown. The same thing with bromine water, it's reddish brown. So when alkanes pass through it, it's going to decolorize, it's going to discharge, it's going to make the reddish brown color of bromine water become colorless. And it's a test for unsaturation actually. In the next video, we're going to look at hydroxylation reaction, a form or type of oxidation of alkanes. Let us now look at hydroxylation reaction of alkanes. Hydroxylation reaction is a form of oxidation reaction. Is that okay? Now when alkanes undergo this hydroxylation reaction, what really happens is the introduction of 2 atoms of OH, that's hydroxyl, into the alkanes. Does that make sense? So just imagine if you're introducing OH into an organic compound, you should be thinking of the concept of alkanol being formed. Is that not so? In the process of hydroxylation, we can use either of these 2 oxidizing agents. We can use potassium permanganate, that's potassium tetraoxomanganate 7. We can use either the acid or the alkaline solution, or we can use peroxymethanoic acid. peroxymethanoic acid is HCOOOH. Then potassium permanganate is KMnO4. Now, when we use KMnO4, that is potassium tetraoxomanganate 7, to carry out this hydroxylation reaction, the ethene alkane, generally, alright, the alkane is converted to diol, the cis form, that is cis diol. That's what we have here. You can say that the conversion of this alkene to the alkanol is either cis diols or trans diols, respectively, the way the statement is put on the board. If you use potassium permanganate, you expect to get cis diol. If you use peroxymethanoic acid, you expect to get trans diol. The concept of cis and trans compound, we've actually discussed that under alkenes IUPAC nomenclature. Remember when we talked about the concept of cis and trans isomers of alkane? They're actually geometric isomerism. Is that okay? So in cis isomer, the functional group, they are attached on the same side of adjacent carbons. You can see that. Look at OH on this carbon, OH on this carbon, on the same side, down, or they can both be upward. Is that okay? On adjacent, close by carbons. But in trans, one of the functional group OH will be down, then the second OH on the next adjacent carbon will be upward, something like this. Does that make sense? So you want to know which one produces cis diol and which one produces trans diol. Once again, potassium permanganate as the oxidizing agent produces cis diol, this one. White peroxymethanoic acid produces trans diol. On the board here, we've used ethane to carry out the reaction equation. So we look at this. This is ethane undergoing the hydroxylation reaction. Like I stated, is a form of oxidation using potassium permanganate here. Of course, if it's an alkaline, potassium permanganate, or an acidified potassium permanganate, the acid there can donate hydrogen, and then of course you have lots of oxygen here already. The hydrogen and the oxygen will combine, OH and OH, two of them, entering into this ethane, break this double bond. Each of them will attach to the adjacent carbon, one in this, one in this. So you have this compound here. This compound is cis-ethane 1,2-diol. It is also known as ethylene glycol. Please take note of this. This compound is very, very important. It is used as an antifreeze agent in car radiators. Please put this down. Write it beside this reaction. Ethane 1,2-diol, ethylene glycol, is used as an antifreeze agent in car radiator. It's also used in the manufacture of terylene. Make a note of this point I just made. Alright, using peroxymethanoic acid, the reaction is essentially the same. The only difference is the positioning of the OH, because it's in trans form, one down, the other up on the adjacent carbon atoms. Please take note of this, because this reagent, potassium permanganate, is also used as test for unsaturation. So you can use to test for the presence of alkene. You can also use it to test for the presence of alkyne, because this reaction will see a corollary of it under alkyne. Now what happens if the potassium permanganate used, the solution is alkaline? The color of this potassium permanganate is purple. But if it is alkaline solution that you used here, the purple color will change to green. But if the potassium permanganate you used here is acidic solution of it, its purple color will become colorless when the alkane passes through it. So take note of this. Refer to it also as test for alkanes. All in all, remember we've talked about using bromine to test for unsaturation. We've also talked about using bromine water to test for unsaturation. In both cases, the reddish brown color of this reagent becomes what? Colorless. And now you've heard about using potassium tetraoxomanganate 7 to test for unsaturation as well too. In the next video, we'll round up with the chemical properties of alkanes, where we talk about polymerization of alkenes.